Okay, we're going to be doing two things today. And they're very closely related. One is going to be, I'm going to start on naming, and there are three kinds of naming. We're going to be doing two this weekend. Today we're doing ionic compounds. Tomorrow we're doing molecular or covalent compounds. The ionic compounds are really important for today's lab on double replacement reactions. And I'll be talking about that as well, but they're closely tied together. The lab is going to be fairly short. It's a good lab. Most people rate it the highest, but they like the most in it. So it's a good lab. I'm glad you're all here. I know after my email to everyone about being sensitive to religious holidays, I'm very both sensitive and aware of that kind of stuff. And I want to make sure everyone has the opportunity to participate in any kind of activity that you may be involved in without being penalized by me. Okay, so any questions about anything? All right, so let's get started then. Of course, they recorded all that very nicely for the world to hear. Okay, well, let's start off by identifying this large group. It's called binary molecules. Binary means two parts. Both the ionic, which we're doing today, and the covalent and molecular tomorrow. Okay, so how do you tell the difference? Because the naming conventions aren't the same. So we've got to be able to immediately identify which one are we working with. Okay, the easiest one is ionic. Basically, an ionic binary compound is in two parts. Okay, so we have a cation and an anion. Cations are positive, anions are negative. No exceptions. You gotta have one of each. If you don't have one of each, then it's molecular or covalent. And that can be two anions, two cations. But to be ionic, you have to have one of each. Now, ions, as you know, are charged. And that charged nature is how we're going to name them. What I mean by that is the molecule has to have zero net charge. That means the positives are equal to the negatives. So when we look at two charged particles, most of the time the charges are not equal. So we've got to play with them to make them that way. Now, let me give you the simplest example. Sodium chloride, common table salt. All right, so let's look on our handy dandy chart here. And do we have, and positive always comes first. So the cation always comes first. So is there a sodium cation on the left side of your chart? Right there, right? Okay, so that's the first criterion. The second one is, do we have an anion on the right side of the chart? And lo and behold, we do. Okay, so that's officially an ionic compound. So to name this, you're going to go sodium chloride. Now, fluoride is not the same thing as chlorine on the periodic table. What's the difference?
The number of electrons.
Yeah, that's exactly the difference. Which has more?
Chloride.
Chloride, because it's a negative charged particle. That means it has extra electrons. Okay, so when you're writing this, make sure you have the "ide" part. The "ide" connotes an anion. Okay, so that's if we had everything as simple as sodium chloride, this would be a very short lecture. But unfortunately, everything is not like sodium chloride. Okay, so let's take another example. Now, I ventured into this a little bit last week. We were talking about single replacement reactions. Remember we talked about the aluminum? What's the charge on aluminum chloride? What's the charge on the aluminum? +3, right? Okay, so here's aluminum way at the top. And then chloride, we already know is at -1. So aluminum chloride is not net zero charge. So we have to do something about that. All right, so aluminum is a +3. Chloride is a -1. So how many -1s do we need to balance the +3? 3. That means it's going to be Al, one of those, and 3 chlorides. So the formula for aluminum chloride is AlCl3. 0 net charge. Okay, now, again, there's no exceptions to this. Now, as a quick reminder, when we first started talking about solutions, what are the two forces that are in play when we were talking about solutions? Do you remember? One was the crystal. Hand out right over there. You see it? One was the crystal lattice force. Remember the other force? Solvating. Solvating force pulled it apart. Crystal lattice force kept it together. There was a battle of the forces. If solvating was stronger, it dissolved in solution. If the crystal lattice force was stronger, it didn't survive or it didn't dissolve. Looking at salt and sand. Sand has a very strong crystal lattice. That's why it doesn't dissolve in water, where salt, the solvating force is stronger than the crystal lattice force for salt. And hence it dissolves. Okay, so when we're doing these ionic compounds, this is going to come into play, these two forces. Now, the handout I gave you last time, that some of you took in lab, is the next handout for today. Now, what I've done, when you get into 1A, 2A, or 3A, they're going to give you solubility rules. Solubility rules are a pain. I did this to get around the solubility rules. This table was built upon solubility rules. So my table was like black and white. What you do is you match up the cation to the anion, bring them together. If it's black, that means it forms a solid. If it's white, it dissolves. No rules. Let your fingers do the walking. Now, in your next class, sometimes they let you use this and sometimes they don't. The rules by which was built are right here. And that's typically what you're gonna have to know. For example, NH4 cation universally is soluble in everything. Sodium is soluble in everything. Yeah, those are some of the rules they come up with. You just have to know those. And you're free to use the rules or the table. Most students like the table. So we're going to be using this in lab today. And in the second part of my lecture today.
Yeah, that's what I read.
Yeah, I really am short.
Right. And the book, they chunk out.
Okay, everyone getting two handouts?
I just got it, yeah, I do.
Someone else? All right. Also, I have the metal activity series from last week. If you didn't get that, that's also up there. Okay. So let's look on the chart here on your, let me take a picture of that. You have two handouts. All right, so here's a solubility chart here. So now let's look at sodium chloride. Okay, there's a column for sodium. I want you to notice that the whole column is white. Okay, that means sodium doesn't form a solid with anything. So if the whole column or whole row is white, that means those ions don't form any kind of solid. So those are some of the rules. It'll say group one. Group one, it starts with sodium at the top. Everything in group one doesn't form a solid. So if you go down there and look at these rules here. Group one elements. Okay, so that's how this table is made. Okay, so we have sodium and we have chloride. So those are going to come together. White box. No solid. Now, there are some gray areas. And the gray areas are semi-solid, and I'm not going to use any of those. I like solid black and white stuff. Okay, but sometimes you can reach a point where, well, it's a little solid, a little gelatinous, you know, that kind of stuff. It'll be gray then, but we're gonna stick to the nice black and white, nice clear cut. Okay, so let's move over to our aluminum. Aluminum was aluminum chloride, right? Okay, so let's find aluminum. Aluminum is over here. So aluminum is fairly soluble until we get down to here. So our first one is hydroxide, the OH. Then it starts forming solids. But chloride is up here. So we have another white box. So aluminum chloride is also going to be soluble. Okay, so does this make sense? Now, when we talk about double replacement reactions, you're going to take one, well, it's going to be droppers. It's going to be the same thing as last week, only with you'll be using droppers still. And then looking at a color change or a not necessarily a color change, but a reaction. Could be bubbles, could be a color change, it could be a solid forming, could be heat, which you can't feel because it's such small quantities. All those are evidence of a reaction going on. Okay. So we're going to have two clear solutions. That means they're in the white. When we put them together, we have two more combinations possible. So we have to look up the new combinations and see whether those are white or black. And that's the idea of a double replacement reaction. Is that what we're doing is we're swapping the cations, we're swapping the anions, but not both, one or the other. It doesn't matter which one. So you end up forming two new ionic compounds. Okay, so let's do some more of this naming stuff here. Okay, is everyone okay with this net zero charge? Does that make sense? All right, so let's do aluminum again. Okay, so let's look at aluminum sulfate. Now notice when I write aluminum sulfate, there's no charge connoted in the name. You've got to know what those charges are by looking on a chart, which I gave you. Now, your next teacher may have you memorize some ions, the common ones. And you know how I feel about memorization. Your smartphone is much quicker than you memorizing stuff. And the smartphone doesn't forget, like you do typically when you leave the class. Okay, so aluminum sulfate, is AlSO4 the correct formula? So we have to look up the charges to determine that. So Al, again, is Al plus 3. And sulfate, you look on the chart on the far right, about halfway down. And on the left, right here. So its charge is -2. Okay, so that's not a net zero. So this is one of those 2-3 things again. Remember we were balancing equations with the same conundrum. What did we do? What's the common denominator between 2 and 3? 6. So 6 is the magic number. How many 3s are in 6? 2. How many 2s are in 6? Notice I have to put parentheses around it. So anytime we have a polyatomic ion, more than one, we have to surround it by parentheses. Even if there's one, if you want to put parentheses in there, that's fine. But parentheses are very important when we're talking about polyatomic ions. There are two positives. Okay, up here at the top, ammonium. She can't see that. NH4. So we're going to be thinking about parentheses for that again. And then towards the bottom here, it's mercury. Those are the only two. There's a whole bunch of them on the right. And very few non-polyatomics. Only the ones at the top. Is anyone in here a OneNote expert? I use this extensively for years, but I have not figured out how to anchor a PDF file so that it always chooses it. Then when I try to draw it, it moves it around. Those are the only monoatomic. Everything else is poly on the negative side. Okay, so that's why we had to use parentheses on the sulfate and so forth. So now we have +6, -6, net 0. Say you made a mistake and you went, oh, it's really 4 and 6 here. Because 4 times 3 is 12, and 6 times 2 is -12, so that's net 0. So, like in a balanced equation, if you have a factor of 2 in there, factor it out. Now, with balanced equations, it doesn't matter if you have multiples, but with writing ionic naming and formulas, it is important to factor it out. Because this represents the actual molecule itself. You could be said to say, okay, do a lowest structure of that. Well, if you got a factor of 2 near, the lowest structure won't be right. So make sure after you do all the subscripts, if there's a factor of 2 in there, take it out. Okay. Now in your dry lab on notation, you can start that this weekend if you want. You don't have to wait for the official dry lab. We have some interesting things going on with the cations. Let's look at lead, for example. Notice there are 2 leads. One's got a parentheses 2, and the other, these are Roman numerals now, the other's 4. Notice the charges on lead, +2 and +4. So that parentheses refers to the charge. Now, there's another name for lead too. It's called plumbus. Plumbic is another name for lead 4. Well, why do we have 2 names? We have something called ancient use of the old names. Plumbus and plumbic are old names. What's the name of a tradesman that works with pipes? Plumber. Plumber gets their names from lead pipes. Also, a plumb bob is also used in the building trade to make sure your pipes are vertical. Again, a reference to lead, because most of the plumb bobs used to be lead. Now, the problem with our industry is that the food industry uses the old names, the agricultural industry uses the old names, not the new names. Analytical chemists use the new names. So if you go gone to your nearest analytical chemistry store, you can ask them for either one and they know what you're talking about. But let's go to Home Depot. And there's something called root killer. And this is what root killer looks like. Copper sulfate. But copper comes in many varieties. The most popular ones are +1 and +2. Which one is it? So which one is it? So it is cupric sulfate, or copper-2 sulfate. Now, we go to the person working in that department. I notice you're out of root killer. Yes, we are, sir. Do you have any cupric sulfate there? Wing right over his head, or her head, whatever. So if you go to a chemical analytical store, they have no problems with all three of these. But it depends on who you're working with, whether they know one or the other or any of them. So if you look on a food label, you will not see copper-2. You'll see cupric, whatever. Ag, you go out and buy some fertilizer. Same thing with them. They use the old names. Now, when I say old names, I'm talking about like old. Alchemy days old. Greek days old. Latin, old stuff. And the problem is cupric doesn't mean, the ick part doesn't mean the same for each one. Same with the us, the OUS. All that means is the cupric is higher numbered than the OUS. But you don't know what the starting is. Where copper-2, you know exactly what the charge is. So it's very, very precise, but unfortunately not used very much. So that's what it is in the chemical industry, food industry, ag industry. They're a very, there's a problem with this naming in our department. Our department doesn't teach the old names, even though that's going to be the most common name you find in real life. I don't know why they'll only teach copper-2. So on your dry lab, you're not going to see any of the X and the S's. You're only going to see the copper-2s and the copper-1s, etc. And I don't know what the justification is for that. I teach it anyway. It's on my common ion chart that I just passed out today. I think it's important for you to know what these are. Real important. Okay, so how are we doing? Are these making sense? Now, the molecular or covalent naming is even easier. There's no charges, nothing to deal with. You're just looking at numbers. That's why if we're talking about molecular or covalent, we're going to be using these names up here: mono, di, tri, tetra, penta, etc. That'll determine how many of them. For example, if we had I'm going to invent some stuff there. Cl5O2. Is that ionic? Is there a positive and negative ion up there? No. So it's automatically becomes covalent, or molecular. So. How many chlorines we got there? Penta, 5. How many oxygens? So pentachlorodoxide. No charges to worry about. And because there aren't charges to worry about, we have to say the number. Now, a common mistake on naming is that students will then say, well, they'll say dialuminum trisulfate. That's wrong because it's an ionic compound. Ionic compounds don't use mono, di, tri, tetra, etc. Only covalent and molecular. Now your dry lab uses the word molecular. Textbooks frequently use the word covalent, but they're one and the same. Molecular, covalent, covalent, molecular, same thing. Okay, so I'm going to do a lot of examples tomorrow on that. Now tomorrow, I'm going to have 2 lectures again, like today. Tomorrow we're going to cover covalent molecular naming and also titration calculations for acids and bases. And that'll put us into finishing this unit. That means the test is not far off. So a week from tomorrow is your next test. Okay? And tomorrow I'll go over a study guide. And then Friday we can review and all that good stuff. Okay, so let's do some more ionic naming here. Okay. Trying to think of some of the oh yeah. What is the name of the ion chart? Top here, what does it say? Common ion chart. That means there's some non-common ones not on this list. Okay. I don't want to publish a book of all the ions possible. These are the ones you run into a lot, but not all of them. So how would you name that? Vanadium sulfate. Now, if you notice on your common ion chart, there are what? 3 vanadiums. Which one is it? There's vanadium 2, 3, and 4. Why 4? So that's, and how many vanadiums are there?
8,034.
Right, and how many vanadiums are in that formula?
1.
1. So that forces the vanadium to be 4. Okay, so this is -2 twice, so that's -4. That forces this to be +4. So this would be vanadium 4 sulfate. All right. What if we had that? what would the formula be? And what would the name be? Okay, what's the charge on two sulfates? -4. And that means we have two vanadiums. Yes, so the vanadium now is vanadium 2 because there's two of them. 2 times 2 is 4. Don't you wish all the math was that hard? 2 times 2 is 4. So it's going to be vanadium 2 sulfate. Now, you need to know formula to name, name to formula, back and forth. For both the molecular and the ionic. Okay, let's see. Something that happens frequently with inorganic chemistry, and we're working with ions. Sometimes the ions, there are different versions of them, and some are more stable than the others. So sometimes you'll have an intermediate version, and there's a more stable version. So it may go from vanadium 2 to vanadium 4, because 4 is more stable than 2. So there's that phenomenon that happens, particularly when we're heating stuff up and then cooling it down. When you heat it up, it's going to be kind of one form. Cooling it down, it comes down and it may change. So it can get kind of complicated that way. But not for our labs. I made them very specific, so there's one or the other. Okay, are there any questions about any naming here? Now the problem, another problem is the names don't necessarily match up to the English names. For example, potassium. Potassium is K. So that's why this chart is very handy, along with that other handout I gave you where you had all the elements and their symbol. So that's a handy chart as well. Okay, so any questions about ionic naming? I've covered a lot of examples for you. Just be aware though, the name of the game in ionic naming and formula creation is net charge 0. That's what rules. And there's no exceptions there. The reason why isolated charges are very unstable in nature. So it always seeks to stabilize the charge. Okay, so let's go on now to, now I'm going to end this video. So you're going to have 2 videos from today. And I getting low on charge here, it looks like 2. Yes, I ended up buying 2 power supplies from my laptop. Because like today we have 22% left. And 22%, it'll probably die in 5 minutes, so. Okay. Okay, so I'm going to